So you saw in that other video, the way that the squeeze theorem works is if you can find something above a function and below a function, and you can find the limit for both of those ones, then you find the one for the one in between. So for example, this f of x graph looks crazy and probably is one that you don't know how to graph off the top of your head. However, there's a parabola on top and a parabola on bottom, and the graph gets squeezed right here to 0. If the upper graph goes to 0 and the lower graph goes to 0, we could say that the graph of f of x would also have to go to 0 at that point. And in fact, that's the only one that you could use the squeeze theorem, the only value. That's the only place it gets completely squeezed out, and you could use the squeeze theorem. So, we've got g of x equals 5 minus x to the 4, and h of x equals 5 plus x to the 4. And we've got some new function, f of x, that we don't even know what it is. But we're told that it's always in between g of x and h of x. Can we use the squeeze theorem? Well, we set it up. We know that the limit as x goes to 0 of g of x is equal to 5. And we know that the limit as x goes to 0 of h of x is equal to 5. We can therefore squeeze it and say, since f of x is always in between them, then as x goes to 0 for f of x, it also has to be 5. So again, if the limit of this one, in this case, was 5, and the limit of this one, in this case, is 5, and if f of x has to be between 5 and 5, it's pretty obvious that it would also have to be 5, right? Like I can do a crazy magic trick. Pick a number between 3 and 3. Did you pick 3? Right, it's not very hard to pick that when there's only one option, right? And that's what the squeeze theorem is doing for us. G of x is 3x minus 4. H of x is x squared minus 2. And we know there's some function f of x that has to be between, always between g of x and h of x. What happens as x goes to 2 for g of x? It's equal to 2. What happens as x goes to 2 for h of x? It's also equal to 2. So by the squeeze theorem, we can say that the limit as x goes to 2 of f of x is equal to 2. So these first two questions, they're relatively easy questions because they gave us both the functions. The harder questions are where they ask you for a limit, and usually these harder questions involve sine and cosine, because you already know sine and cosine have to be between -1 and 1. From that, you try to make a squeeze theorem out of it. So that's what our next example looks like, okay? We want to find the limit, and this is one very similar to what we did on the video with Mr. Bean, right? I think he had 1 over x squared, we have 1 over x cubed. Okay? You know this, that cos of x is always between -1 and 1. And if you start with that, what we want to do is create this equation. So what could I do to create that equation? Well, if cos of x is between -1 and 1, then cos of 1 over x cubed is still going to be between -1 and 1. there's no way that you could put anything inside of cos to change that. And now, to get that equation, we multiply everything by x squared. So we know negative x squared is less than x squared cos 1 over x cubed, and that's also less than x squared. Then if we find the limit as x goes to 0 of the left side, and we find the limit as x goes to 0 of the right side, and they're both 0, we can say that we can figure out the limit of this. What's the problem with trying to do it directly? You're not allowed to plug in 0, right? If I plug in 0, I have an issue. The issue is I can divide by 0. And there's no amount of algebra that we can do to this equation to get rid of that. We're just sort of stuck in an algebraic perpetual problem. So here comes along the squeeze theorem to help us with it. Just like cos, does it make sense that sine is always going to be between negative 1 and 1? And so sine of 8x would have to be between negative 1 and 1. Can we plug in for this one, though? Can you do sine of 0? What's sine of 0? It's your y-coordinate, right? Your y-coordinate would be 0. And can you do 0 times 0? Yeah? Just check your times table. You still good with that? Okay. This one, just telling you, we could plug things in. The previous one caused a problem. Okay. This one, technically we could plug things in. I already know the answer is 0. I'm going to do it with the squeeze theorem to prove it again. But this one you don't need the squeeze theorem for. If you can plug it in, is sine 8x a continuous function? Sine graph you can draw without lifting your pencil. If you multiply it by x, is there any non-permissible values in this at all? No. So you would be able to just plug it in and say the limit is 0. Sometimes when we learn something new that's complicated, we now use the complicated technique rather than the easy one. This one is an easy question. But if you went this way, it's not wrong, right? I can multiply both sides by x. What's the limit as x goes to 0 of negative x? Obviously 0. What's the limit as x goes to 0 of x? Obviously 0. So this limit would equal 0 as well. Sometimes it's fun to see the graphs. See that it's always in between them? Which is kind of cool. But didn't need the squeeze theorem for that one at all. When do we need things? When we run into problems, like right here. Can I plug in 0? No, I run into a problem. If I get something that's 0 over 0, problem, right? Then we need to use our other techniques. But be careful, because sometimes there's easy questions where no complicated techniques are needed. Now, here are two new formulas. You will have to have these two new formulas memorized until we learn a new advanced technique which makes learning these formulas so easy you won't have to memorize them anymore. But you don't know that technique yet. So at this moment, you have to have these two new formulas memorized. What happens if I plug in 0? I'd have 0 on the bottom, that's bad. I'd have 0 on the top, that's bad. Right? And in this situation, 0 divided by 0 happens to equal 1. And there's a nice proof in your textbook that shows you how we're not going to do that. If you want to look at it because you like math, you're like, ooh, I want to see this. It looks cool. It's pretty Like, they had to be pretty creative with the squeeze theorem to make this work. So it's kind of elegant and beautiful, but complicated at the same time. So if you have time, you can look at that in your textbook. And here, what's cos of 0? It's 1. So 1 minus 1 would be 0. And if I plug in 0 on the bottom, I get 0 again. And this time, 0 divided by 0 is 0. For sine, 0 divided by 0 is 1. For cos, 0 divided by 0 is 0. And again, there is a proof of this in your textbook. But you have to, at this moment, know these two formulas to be able to solve, and we're just going to do a couple, to be able to solve questions like this. And then after we do these first two examples, I'm going to show you some AP-style multiple choice questions where these come involved from the AP question. So, limit as x goes to 0 of sine 8x over 8x. What we can do is pick another variable, t, theta. If you really like w's, go for it. If I let t equal 8x, does it make sense that as x would go to 0, t would also go to 0? Okay, it's not crazy hard, but this is important because I'm going to change this equation, sine 8x over 8x, as x goes to 0, to sine t over t as t goes to 0. Because then it matches up perfectly with my formula. And then this is going to equal 1. So this is going to equal 1. As a general idea, if you have the limit as something goes to 0, I'm going to represent my something as a green square. And you have sine of something divided by that something, it will always follow this formula and be 1. Okay? I'm actually fine if you would just take this and right away we'll write 1. You wouldn't have to do this substitution. I'm showing you the substitution now to get you the idea. Okay? But does it make sense that if you have these somethings? Okay? Now, as x goes to 0, does something go to 0 as well? Right? It's not exactly the same here, right? Because we have the something, but this is different. But if x goes to 0, does 8x go to 0 as well? Right? Yes, it does. So we have this idea. I'm perfectly fine with you changing that to equal 1 right away. What are we going to do here? Because we have the something, but I don't have the same something on the bottom. So we need to get a little bit creative. How could I get a little bit creative? Oh, I don't even want to hit boxes here. I just want to play with this. Okay? Well, I'm going to play around with this. This is going to be fun. Playing with math is always fun. Like, this would be easy if there was a 2x down there, right? Wouldn't that be nice if there was a 2x down there? Because then it would match up nicely. Okay, I don't have that 2. I'm going to add that 2 down there. Mathematically, am I allowed to do that? Absolutely not. Unless I also put a 2 there. Do you see those 2's would cancel out? And you have exactly what you started with. In fact, I'm sort of doing this, like a common denominator thing. I want a 2 on the bottom, so I multiply 2 on the top. You have a limit rule that says If you can find the limit of this 2 inside is the same as taking that 2 outside. And if I put the 2 outside and this limit is 1, okay, here's the idea. This limit should be 2. Right? Because if this limit is 1, and I'm multiplying it by 2, then that limit should be 2. If we wanted to do some formal stuff, we could let 2x equal t. As x goes to 0, t goes to 0. I do this 2 and 2, and then I get the limit as t goes to 0 of 2 sine t over t. I can limit law says I can bring that 2 out in front, and I get 2 times 1, which is 2. And the next ones add some complications. We're going to leave them till next week. Feel free to see if you can play around with them, right? Because if you play around with them and you figure some stuff out, that can be very fun. Take out some scrap paper. See if you can get strategic on what you would like to do. And we'll figure those ones out. But right now, we're going to stop our video here.